Hey, so today's lesson is on conductors and insulators. You've probably heard of these words before, but we're going to look at them a little more detail and try to relate it more to electricity. Okay, so conductors. Uh, a good conductor, you can see all these pictures up here. They're all different types of metals. Okay, metals are usually your good conductors. Okay, they can conduct or carry electricity. That's what it means if it's a conductor. Has low resistance. And remember, we think of the word of resistance as a almost like friction. Okay, so they have low friction within it. So when electricity travels through, the materials can flow easily. Okay, when you think about a metal, they have electrons that can kind of bounce from one atom to the other, which allows the current to be carried. Oops. So examples: silver, copper, gold, aluminum, iron. These are all examples of good conductors. Okay. Insulators. So insulators, again, up here you see rubber, glass, oil, diamond, dry wood. Okay, these are things that do not allow current to easily flow through them. They have high resistance. Again, examples. Now, here's one that's not listed up here, but air. Okay, air is a really good insulator. We don't always think of that being an insulator because when you look outside in a thunderstorm, you see lightning, and the lightning travels right through the air. It doesn't like to do that, though. Air is not a good conductor of electricity, so the lightning will find the path of least resistance to the ground. That could be a building. That could be a tree. That could be a metal pole. Sadly enough, that could be you if you're standing out in the middle of a storm. It will find a path that's going to get to the ground as fast as possible. And air is not the main thing it's going to pick. It's going to try to pick something else over air because air is an insulator. It's not, it causes, it's very high resistance. It's not going to allow it to flow. Okay. And when we think about conductors and insulators, we kind of separate them by objects that are good insulators and objects that are good conductors. When in actuality, we kind of have to think of it like objects that cause a really high resistance, which is insulators, and objects that cause really low resistance, which we would consider conductors. Okay, all of these things, rubber, glass, oil, diamond, dry wood, all of it can conduct electricity, but it's very high resistance. So it does not, it does not allow low amounts of electricity to go through them very easily. Okay, that's why in your house you have a wire that you plug into the wall or something. It's got a rubber coating around it. Okay, that's to protect you because rubber is not a good conductor, and with the low amounts of electricity flowing through that wire, it does not allow the electricity to easily flow through that wire or through that rubber casing that's on the outside. Okay. Now, on the other hand, if you look out at high tension wires or the electric wires that are up on the poles, okay, those have an extremely high amount of current going through them. So therefore, those wires, even though they're cased in rubber for the most part, they have a rubber casing on them. If you were to touch it, you would get shocked. Okay, the electricity would still flow through that. That's why if you ever see power wires down or anything like that, you don't go and touch them. You don't try to move them. You just leave them be. Then we got semiconductors. Okay, they kind of are exactly what they say, semiconductors. So resistance in between a conductor and an insulator. They can conduct some current. They're medium resistance. Examples, it says, are carbon, germanium, silicon. And silicon is used in computer circuits. Okay, so these are used where you just want a small amount of current going through. They allow current to flow through. They don't heat up quite as much as things that are low resistance, or I'm sorry, of high resistance. Okay, so they're medium. They're kind of in between there. Wires. Okay, so if you look here, you have some pictures of some wires up at the top. Okay, the wire has an insulator. Each of these wires inside of the one big protective sheath all have their own little protective sheaths. Okay, usually color coded. Okay, the wire itself is the conductor that allows the electricity to flow through. The outside is the insulator, that little bit of rubber. Okay, the rubber between these wires are keeping the electricity from flowing from one to the other. If this breaks, you could have what they call a short in the wire, where electricity is going to just flow right from one wire to the other and go right back to the source. And that's going to cause, usually, could heat up enough to set a fire, or melt, or might pop the circuit breaker. Okay, and then you have the outside. This is what's protecting you from the wires themselves. Okay. Over here, copper conductors. These are the little pieces. It can be frayed, like real thin wires like this that are kind of bound together, almost like how a rope is bound together with minor threads, or it could be one big piece of wire. And usually, the wires in our houses are made of copper, and then in smaller electrical devices, it might be made of other materials. So, made from conductors and insulators, a metal conductor surrounded by an insulator. The insulator keeps the current inside of the wire, reduces the risk of electric shock and fire, and allows wires to be packaged together. Okay, meaning these, how they're packaged together up there. Okay, but like I said, if a high amount of current was going through, it doesn't matter if you have an insulator going around it, the electricity could still go through it. Okay. But in our house, we only have 120 volts of electricity coming out of our outlets. It usually does not cause enough current through the wire itself that would cause you to be shocked. And it's going to follow the path, the least resistance as well. So it's going to follow the path of the wire and not go through the rubber. Okay, resistors. They almost look like, if you ever look, I'll show you. You'll see a picture of it in a little bit, but it looks like like a little ball or little cylinder that's on a wire itself. Okay, you might see it if you ever looked at like a motherboard of a computer or different circuitry in electric devices. Okay. Resistors are used to control current in circuits. So when you have a whole circuit on like a motherboard or something, you need to lower the current going through certain parts of it. So the resistors are used to control that. Okay, things such as TVs, computers, phones, appliances. All these things would have conductors. Even some lamps will have some of these lamps will have a resistor attached to them to lower the amount of current that's going to go through that lamp. Objects can vary in resistance from small, 0.001 ohm of resistance, to very large, up to 1 million ohms. Electrical devices are designed with a resistance that causes the right amount of current to flow at certain voltage. Okay, so all of our electrical devices that we're plugging into our outlets are designed to have 120 volts of electricity. Okay, if for some reason you had an outlet that was more than that, it would damage or could damage the electrical device. Okay, and that's why when you go, if anybody's ever been overseas, you go over to Europe or something like that, theirs are 220 volts. Their plugs are also shaped different than ours, so you have to get a special adapter to plug ours into theirs, and it just changes the amount of voltage. It adjusts the voltage so that way when you plug in your electrical device that you brought from America, the voltage going into it would still be 120. Okay. Same with different things with batteries. Each battery, every little battery is 1.5 volts. When we're talking about the little round cylinder batteries, then you also have 9-volt batteries, which are like the square ones. Okay, those 1.5 volt ones, sometimes you'll have them lined up together, and then each of the voltage adds up. Okay, but if you somehow put different voltage in, or you flip the battery a different way or something, you could damage the circuitry. Light bulbs and resistance. Okay, it says a 100-watt light bulb has 145 ohms of resistance. When connected to a 120-volt outlet, it draws 0.83 amps of current, enough to light it up. Okay, if you put that same lamp or the same light bulb with a 1.5-volt battery, it's going to draw only 0.01 amps of current, which is not going to be enough to light it up. Right? So it all depends on how much voltage is going to go through and what the device that you're using is asking for. Okay, resistance on skin. So on dry skin, it is 100,000 ohms of resistance. So we have a lot of resistance on our dry skin. Okay, but wet skin, it drops down substantially. It goes from 100,000 to only 1,000 ohms of resistance. So your resistance gets less when your skin is wet. Okay, that means that electricity goes from being, not flowing through very easily, tons of friction, lots of resistance, to not much resistance at all. Okay, so why is it dangerous to touch a wall outlet, but not necessarily a battery? Okay, and we're not talking a car battery. Car batteries are a little bit different. Okay, we won't just talking about a regular normal battery. Okay, so in this case, we got a 9-volt battery, which sometimes if I want to see if a 9-volt battery even works, sometimes I'll stick it on my tongue, which probably isn't the best idea, but it will give you a little shock and you see if the battery works. Okay, but that's mostly because it's not going to cause a lot of current. Okay, so you got a 9-volt battery. You got 100,000 ohms of resistance. Okay, remember the formula V equals I times R. Okay, so if we are solving for I, you're going to, at this point, divide both sides by 100,000. So 9 volts divided by 100,000. So that gives us 0.00009 amps. Very, very small amount. Again, this is on dry skin. Okay. A wall outlet. Now you got a wall outlet, 120 volts, 100,000 ohms of resistance. We solve it the same way. Okay, 120 divided by 100,000. We get 0.0012 amps. Okay, that looks very small. Okay, but it could potentially harm you. If you had a heart condition or something like that, it could potentially kill you. If you were somehow stuck to it or something like that, you couldn't get off of it, because a lot of times when you get shocked with electricity, your muscles will tighten up. You could be stuck to whatever is shocking you. Okay, and it could potentially kill you. Usually it takes about 0.01 amps to fully kill someone. So if someone were to, accidentally stick their finger in an outlet, or if they stuck not that you stick your finger in an outlet, but if you stuck your hand in where a light bulb is and the light bulb's not there or something, usually you'll get shocked and it will hurt and it will knock you off. But it usually won't kill you. Okay, that's with dry skin. Okay. Now we look at when you're wet. Okay. So again, with dry skin, 120 volts. We went through this already. 0.0012 amps. Okay, quite a bit of, current, but still probably not going to kill you. Could kill you, but maybe not. And then you got wet skin. Okay, now you got only 1,000 ohms of resistance. Okay, 120. You're going to divide that by 1,000. Now you got 0.12. Okay, that's 10 times the amount of current that could possibly kill you. So you go from dry skin, it's going to hurt, but probably not going to kill you. Okay, to wet skin, and it's without a doubt most likely going to kill you. Okay, that's why you'll see. You probably, as a little kid, at least I remember the story of don't put the toaster near the bathtub. I don't know why a toaster would ever be near a bathtub, but if the toaster falls in the bathtub, the person's going to die. Same with a hair dryer or anything else. Okay, because it's going to cause a major increase in the current. Okay, one good thing, which doesn't mean it's going to save your life, but most wall outlets near water, which would be in your kitchens, in your bathrooms, even outside where it could be rainy, something like that, they have what they call ground fault interrupters. And what that does is, in any change in current, any quick change in current, it's going to pop the switch. So it's going to cut off that power immediately. So you will still get hit with quite a bit of current, but it wouldn't be consistent, so it wouldn't be over a long extended period of time. Where your regular outlets, they will eventually pop a circuit breaker, but that circuit breaker, in order for the circuit breaker to pop, there has to be enough increase in heat for that to pop. Okay, if it doesn't heat up enough, it won't pop right away. So it takes more time for a circuit breaker to pop. And inside of that circuit breaker, there's a piece of metal, and that metal, when it heats up, expands, and then as it expands, that's what makes the circuit breaker release. So it takes time for that. Well, if you're getting electrocuted, you don't want it to take very long. you want it to pop very, very quickly, or else you are guaranteed to die. In this case, like we said, most likely you would die from this type of this much current going through you. But the ground fault interrupter will hopefully stop it very quickly, give you at least a chance. So. Okay, changing resistance. Says resistance of electrical devices can vary. Temperature is a big increase, or causes a big increase in resistance. As a wire heats up or anything heats up, that resistance increases to the point where the temperature of the wire will get hotter, and then the resistance gets greater and greater, and it's kind of like a double-edged sword there. Okay, so as one gets hotter, the next one it gets more resistance. As there's more resistance, it gets hotter, and eventually the wire would melt, which can cause a house fire, things of that nature. Okay, it says increasing current can cause increased resistance. So both of those things kind of go hand in hand with each other. Okay. There are other, things called superconductors. A superconductor is a material that actually, when temperature is decreased to extremely low amounts, the temperature, or the superconductor resistance will drop to zero, which is pretty cool. Now we're talking extremely low temperatures, but at those low temperatures, there's zero resistance going through whatever that material is that they're using as a superconductor. So something, if you ever wanted to research a little bit more, superconductors are pretty cool. They do some really cool things, levitation, magnets that can levitate, and things of that nature. So if you have time, look up superconductor, look up some videos of them. They're pretty cool. Okay, so these are pictures of fixed resistors. This is what I was talking about. It looks like a little cylinder thing going through. You might see them in circuitry. Have resistance that cannot be changed. The colored bands are a code that tell you the amount of resistance. So each one of these little colored things, actually, there's like a key that you can look at to figure out exactly how much resistance each one of them are. Okay. Variable resistors. This would be something that as it spins, it changes the resistance. Okay. So examples of this would be dimmer switches, volume controls. When you're turning up the volume, decreasing the volume, that increases or decreases the current going through based off of the resistance that is there. So, increase in resistance is going to cause a decrease in current. Okay. So when the resistance of the dimmer switch increases, the current decreases and the bulb gets dimmer. When the wiper is moved, the resistance changes. So as this little wiper thing in here, these pop-ups. Okay, as this wiper goes back and forth, okay, that increases or decreases the resistance. Okay, so what happens to current if a circuit's resistance increases? Okay, so as the resistance increases, the current decreases. Okay, and vice versa. List the units used to measure resistance, voltage, and current. Okay, so resistance is ohms. Remember, that's the funky looking, looks like an upside down horseshoe, okay, or a hat. Voltage is volts, current is amps. Then we classify as a conductor, semiconductor, or insulator each of the following. Okay, so air, remember we said air is not a good conductor of electricity. Okay, it is a good insulator, so it's high resistance. Gold is a very, very good conductor of electricity. Okay, Silicon, that is what's used in computer chips. That is a semiconductor. Okay, it uses it does not allow or it's medium resistance, I should say. Sorry. And then rubber is an insulator. Aluminum is also another conductor. Okay. Okay, so now it is your job to complete the conductor and insulator quiz that you will be given.